Okay, everybody, welcome to Control System Analysis and Design. It's AE 430 at AE 430 is the class. If you've never taken this class, I'm actually taking it at Embry-Riddle. So what we're going to do here is a standard controls problem of taking the stiff EQ and representing it in a state space matrix system. So going through here, what you want to do whenever you're breaking down these types of equations, the main point is to isolate the highest derivative on the one side completely by itself in order to continue from there. So I'm going to go ahead and do that for equation 1 and equation 2. So for 1, you're going to end up with theta double dot 1 is equal to 10 over 3c minus 100 theta 1 plus 100 theta 2. And then you're going to divide that all by 100 over 9. And that's your first equation. So pretty easy so far. If you go ahead and simplify that even a little bit more, you'll end up with 3t minus 9 theta 1 plus 9 theta 2 is equal to, I'm going to leave that blank here for a second. Just remember, we're going to set it equal to something a little bit different than theta double dot 1. Okay, moving on to the second equation. Theta 2 double dot is equal to theta 1 minus theta 2 dot minus theta 2. And that's completely simplified also. As you can see, I probably skipped some. No, I didn't skip any steps here. Just move everything over there and then divide by 100 and you end up with this. This is also going to be equal to a mystery value that we're going to get to here in just a second. So, whenever you're setting up something inside of a state space, you have to identify your states. In this case, we have theta 1 double dot and theta 2 double dot. Once you have it in this form of equations, it's really easy to see how many states you have. So, since this is double dot, we have 2 states for theta 1 and then 2 states for theta 2. So in order to get all the states, we're going to have x1, x2, x3, and x4. And these are going to equal theta 1, then theta 2, then theta 1 dot, and theta 2 dot. Equal, 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 equal. Just like that. And now you have all your states identified as a single variable, basically, or something that can be put into a single vector. So then moving on from this, in order to encompass all the different states that we have here, so like theta 2 double dot, in order to represent it as an x, we're going to go ahead and take x1 dot is equal to theta 1 dot, which in turn is, we find, is actually equal to x3. And then we've got x dot 2 is equal to theta 2 dot, which is equal to x4. And then x3 dot is equal to theta 1 double dot, and x4 dot is equal to theta 2 double dot. So these two values, as you can see, since they're equal to theta 1 and theta 2, we know that x4 dot is going to go up here, and x3 dot is going to go up here. So these are the two equations that you're really going to care about here as we start going into the state space matrix. Okay, so now laying out our state space, we have x1, x2, x3, oops, get it up here where you can see it, x3, x4, all of them dotted, going like this. And then this is equal to our A matrix. So, to fill out the A matrix, what you're going to have to do is go up to these equations again and replace each one of these values with the x that it represents, and this will help fill out the matrix. So I'm actually going to extend this a little further. This is not the most important equation. The most important equation is what comes after this, when you realize that this is equal to x1 minus x4 minus x2. And this is replacing each one of these thetas with their respective x that we defined down here. So this is your most important equation. And then up here, this one, I'm actually going to move. I'll squeeze it in here, sorry. This is equal to 3t minus 9x1 plus 9x2 right here is equal to x3 dot. And there you go. That's your equation right there. So this equation and this equation are the ones you're going to really need. So laying out this matrix down here, if you want to look at it like this, is you want to define the equation for x1. Now in this case, x1 is equal to theta 1, which is basically x1 is equal to theta 1. So for x1 dot, you're going to end up going 0, 0, 1, 0. For x2 dot, you end up with 0, 0, 0, 1. And you can label this as x1, x2, x3, x4. And I'll define these, explain this a little bit more here in a second. Alright, for the x3 dot, well, you have this equation right up here. x3 dot is equal to something, all the values for the x that we have in there. We're going to ignore t for a second because that comes in a minute. That's going to be negative 9 for x1, 9 for x2, and then for x3 we don't have anything there, so that's going to be a 0. And then for x4 we don't have anything, so that's going to be a 0. So that all came from this equation right there. Alright, so then moving to x4, x4 is equal to this right here, so we have 1 minus 1, 0 minus 1. So this is a negative x to the fourth, so on and so forth. So, and then the x1 dot is equal to theta 1, which is equal to x3. So the x3 is right there, and then x2 dot is equal to, excuse me, x2 dot is equal to theta 2 dot, which is equal to x4. So that fills out your primary A matrix. Moving on to the C matrix, you know there's nothing from there, there's nothing from there. This equation actually has an output of t. So we're going to go ahead and put 3 in there, because that's t. And t we're actually going to define as u, which is your output. And you'll see where that comes in just a second, because your C matrix is multiplied by u. And you can make that t if you wanted to, but this is just your input. Then moving on to the output, this is equal to 1, 1, 2, 3 times x bar. And where did this 1 come from? 1 for x1? Well, if we're trying to find x1 out of this, if the output of the system is theta 1, then we'll want to define x1 as the value that we want to get out of here. So x1 is equal to theta 1. So x1 is 1. This will give you the output of x1, which is theta 1. And then plus 0 u. And you're done. So that's your 2 differential equations represented in state space.